All right, everyone. Here is your video for this particular week. It's got some very important information on this. Please make sure you do watch this to the end, okay? What we're going to be covering this week is only two sections, so you'll only have two sections of check your understanding questions to do as well. But that will be it for this week. So first, we're going to be talking about topic 7, estimating means and proportions, and topic 8, margin of error when making those estimations about population means. They're very, very similar, but they're a little bit different, and I'll explain as we go through. Now, one of the first things that we need to talk about is that there is going to be a grading change. As you guys notice, I have talked a little bit about how some of the students are not um, answering the check your understanding questions in the correct manner. It's very easy to tell what these students are doing. All they're doing is they're whipping through the questions as fast as they can the first time, seeing what the correct answers are, and then turning right back around and answering them again. Um, I've just seen multiple students still, even after we talked about this last week, that they are just getting, a 0 on the first attempt in less than a minute, and then a 100 on the second attempt in less than a minute. That again is unacceptable, and from now on, that will not result in a passing grade. So I wanted to explain how that's going to work. So here is the update. All valid attempts will be graded as before. So you'll get a 100 for all three right, an 85 for two right, and a 70 for one right. You can do the questions as often as you want. A major part of this, though, guys, is your first attempt really, really, really has to be a valid attempt. A valid attempt is one where it takes you a reasonable amount of time to answer the questions. I do all of these questions before you guys do. I've taught Algebra 2 for years. So no one should be able to answer these questions faster than me. So I track how long it takes me to go through those questions. It needs to be a reasonable amount of time. Less than a minute, 1 minute, 2 minutes, 3 minutes, 4 minutes. That is not possible for anyone in this class to read through all three questions and answer all three questions correctly, including the amount of time it takes to do calculations, because sometimes they have multiple, answers within each question. Again, you know, valid attempts only are going to be graded here. So what happens to an invalid attempt? Well, you'll be given a semi-permanent failing grade for that assignment. What I mean by semi-permanent is the second point. In order to improve this grade, you must contact me through Remind or email to explain why you think your attempt was valid. Um, it does not matter how many times you take it. It doesn't matter how many times you get a 100. If you do an invalid attempt, your grade, that failing grade that gets put in, will not be changed until I hear from you through either Remind or email. So here's a couple examples of some invalid attempts: 0 or very few minutes on the first attempt. Guys, your first attempt is really the one that kind of tells me whether you are really actually attempting to do the questions correctly. Um, no student should ever have a 0 or 1 minute or 2 minute attempt on all three questions. That should just not happen. You're not trying whatsoever. You're not taking notes on the videos. That's what you should be doing. I mean, you're going to have a test on this stuff coming up soon, or a quiz, an assessment. And of course, you're allowed to use your notes on it, whatever you took. But um, as we get to the end of this particular module, just, you know, spending 0 minutes watching the video and then 0 minutes doing the questions is not teaching you how to do the topics on here. That's not, you know, that's just not the way to do this. The other thing that I get kind of goes with this one. I get students with a very short first attempt, followed by a 100 on a very short second attempt. Again, same thing. All the students are doing is whipping through, getting the answers, and then just typing them right back in. Um, And then basically any other attempt that I decide is invalid. I don't know what this could entail right now. But frankly, I thought I'm picking up all of these, but if I notice another trend, well, that will be something else. All right, so we'll just have to see how it goes. All right, so getting into what we're doing this week. Again, there's only two topics this week. The first one is topic 7, estimating means and proportions. So what we got here is Mr. Howe has 18 students in his Algebra 2 class. Each student chose a partner, and each pair was given a bag with 50 jelly beans. Each bag had a different population of green jelly beans. In other words, the students don't know how many jelly beans, how many green jelly beans are in each bag, right? So they had a different population. So what they were doing is the students were drawing out. The students simulated drawing 50 different random samples of size 50. So in other words, they pull a jelly bean out, look at it, see if it's green, mark it down whether it's green or not, and then they put it back in. Jumble up the bag, they reach in, grab another random jelly bean, and then they continue to do that. They repeat that 50 times. Okay, and what we have here is some graphs of how that works. So in a bag that had 10% of green jelly beans, so in other words, if there was 50 jelly beans, 5 of them were green. 3 times it looks like they pulled only 2 green jelly beans out. A bunch of times here, it looks like they pulled out 3. A bunch of times they pulled out 4. A bunch of times they pulled out 5. And then over here at the end, only 2 times did they pull 10 green jelly beans out. All right. And so on for 20%, 30%, 40% population. So when we get up to, let's say, a 50% population, that means 25 of the jelly beans were green and 25 of the jelly beans were other. And then they did that all the way up to a 90% population. And as you see, these graphs are slightly moving to the right. And also one thing that you should notice is these graphs here are kind of following the normal model a little bit. Again, that's kind of what happens. You get the thing that comes up the most should usually be in the center or close to the center. It's not always exactly that way, but that's the way it kind of should be, somewhat mound shaped. Okay. So it said after the class simulation, Mr. Howe gave a surprise bag to Myra and Hassam with a percent marked on the bottom. They drew 31 green jelly beans and a random sample of 50 from the surprise bag. So what populations could this surprise bag come from? Well, if we go back and look over here, so 31 is over here. So definitely there's just no way that that was a 10% population jelly bean bag. There's just no way. I mean, 31 is way over here. Could it have been a 20%? Probably not. 30%? Probably not. 40%, it's getting closer, but again, 31 is still over here. So if it didn't happen in the first 50 times, the first 50 experiments, it probably isn't going to happen in the 51st. So here we can see, hey, look, in a 50% population jelly bean bag, 31 did came up one time. All right. 60%, yeah, 31 came up a bunch of times. And we go to 70%, yeah, 31 came up a couple times. And then by the time we get to 80%, it's, our possibilities have kind of like passed us by. So that tells us that that mystery jelly bean bag is probably between 50 to 70% green jelly beans. All right. So we would go over here and we say, hey, it's from 50% to 70%. Okay. So it says consider a random sample that reasonably comes from the population of 20% to 50%. This is sometimes rewritten as 0.35 plus or minus 0.015. The value 0.15 is called the margin of error. So let's talk about this right here. So if you had something that could possibly have only been from 20%, 0.20 to 50%, 0.50. Another way to think about this, besides thinking about, hey, it goes from here over to here, is we think about the center. So the center is 0.35, and then we can go 0.15 this way. So 0.15 minus from 0.35 would be 0.20. Or we could go 0.15 this way. and 0.35 plus 0.15 is 0.50. So there's two different ways to think about, you know, this, whether we're going to do a range from here to here, or whether we're going to talk about the center and then how far it could go in either direction. So those are the two ways that we can think about this. So if we look at this previous answer, we said that the population was going to be somewhere between 50% and 70%. All right. So one way we could say is that it's between 50% to 70%. But another way that we can think about that, guys, think about what is the number that's in the very middle of 0.50 and 0.70, and that is 0.65, and then that would be plus or minus, yes, 0.65, 0.15. So these are the two ways that we can talk about it. That that mystery jelly bean bag was between a 50% proportion and a 70% proportion of green jelly beans, or we could say that it had, we believe it to be a 65% proportion jelly bean bag, plus or minus 15%. So there's two ways to think about it. And again, this right here is called margin of error. We call it MOE for short sometimes. All right. So, Mr. Howe introduced a second surprise bag. Students drew 22 green jelly beans this time in a sample of 50. So, let's all do the same information that we had before. All right, so 22 green jelly beans. So, we go down and we see, could it be 10%? No, 22 is way over here. How about 20%? No, 22 is still over here. Could it be 30%? Well, here's 20. Here's 21. Here's 22. Yeah, it could have been 30. That's okay. Again, here's 22 right here. Even though 22 never got picked here, it's still within the range. So that's a good one. So 30%, 40%. 22 still in the range here. So 50%. And even 60%. Yeah, that's okay too. So it's going to be somewhere between, and then once we get up to 70, we can see the 22 is way down here. So we're way past it now. So it's going to be somewhere between 30 and 60%. All right, so we'll go back over there and we're going to write this, it could be from 30% to 60%. No, I think it was 70%, wasn't it? It was, no, 30 to 60. I was right the first time. All right, 30% to 60%. So how do we write this? Well, we could be it's 0.30 to 0.60, or we could write it, what would be the middle number between these? Well, if you're not sure, you can add them up and average them. So that would be 0.90 divided by 2, so it would be 0.45 plus or minus 0.15, because that's the number that you add and subtract to 0.45 to get to these two extremes, right? And the margin of error here would be 0.15 or 15%, or however you wanted to write that particular number. All right. Okay, so there's another method we can use to determine margin of error as well, all right? So sometimes we don't have, that data that was shown to us. So it says the formula for the approximate standard deviation of the distribution of sample proportions is given by this. So what this formula is going to do is it's going to find the standard deviation using some information that's given to us, all right, as far as like percentages go. P hat, that's what this is called with this little thing on the top. P hat is the sample proportion, and N is the number of samples. And we're going to kind of shorten this up a little bit in a minute. I'm going to show you the version that we use in AP Stats because it's very, very simple. But it says, and we're going to put these two things together, this piece here and this piece here. And it says in normal distributions, 95% of the sample proportions lie within how many standard deviations of the population proportion? Well, here is the chart right here, the normally distributed bell curve. And really, when we start here at the mean, we go one standard deviation to the right, one standard deviation to the more to the right, and then one more. So we go up 3, and then we go down 3 through subtraction. Where we really care about this data, guys, is from here to here. This number right here is the number that we use most of the time, because you guys can see that includes most of the data. The only data that's not really included is this extreme data that's out here, and some also very, very extreme data that's way out here. There is extra data as this goes out, but the vast majority of data is included within this, portion right here. So we're going to say that this is within 2 standard deviations. So what we're going to do is we're going to take this number here, and we're going to take this formula here, and we're going to put them together, and what that will give us is that will give us something called margin of error. All right, so here's an example. The Student Government Association at Crestview High School surveyed to determine if they would rather have a coffee stand or a frozen yogurt stand during lunch. 130 out of the 200 randomly selected students said that they preferred a coffee stand. So it says determine the interval that represents the margin of error. So we're going to go ahead and do this particular thing here, all right? So the P hat is the proportion of students, and I guess we're going to go with coffee stand because that's the one they said, coffee stand here. So 130 out of the 200. So we could take this formula here and we go, all right, 130 out of 200. That would be the proportion of students that preferred the coffee stand. And then we do 1 minus that exact same number, 130 out of 200. And then over that, or under that, we put 200. This is the sample size. This number here is going to be the same, and then we take the square root, okay? So when we do this formula, this is going to give us the standard deviation. Well, remember, the margin of error most of the time we want is 95%. So how far do we need to go out from the center? We need to go 2 standard deviations to the left and 2 standard deviations to the right. So if we multiply this whole thing times 2, that is going to give us our margin of error, all right, for what we call a 95% confidence interval. We'll talk a little bit more about that, but this is kind of, I don't like the way this question is written because they don't really explain too much about that. So if we throw this into a calculator, we've got 130 minus 2, or 130 over 200. So in a calculator, that would be 130 divided by 200, and we get 0.65. All right, in other words, 65% of the students wanted a coffee stand. Now, I want to take that and I want to multiply it times 1 minus this. Well, if this number is 0.65, I just have to remember 1 minus 0.65 would be 0.35. All right, and that's really the other formula that we use in AP Stats. We change this 1 minus P hat right here to a different thing called Q hat. And it's not really a big deal. It's just whatever is the other number that gets this up to 100%. So really what this would look like is this would look like 0.65 times 0.35. And again, how did we get to 0.35? Well, we did 1 minus this number over 200. Then we're going to take the square root and multiply times 2. Okay? So calculator, 0.65 times 0.35. Let me move this over so you can see. Divided by 200 gives us this value. And then we're going to take the square root of that value. And then we're going to multiply it times 2. And we get this 0.0674. Remember, this is a percentage, all right? And we'll do, I don't know, maybe 3 decimals, all right? 0.067. This 4 right here says to the 7, hey, stay there. So really what we're saying is we are saying that 0.65, in other words, 65% of the students said they wanted a coffee stand, plus or minus. And then we can say 0.067. In other words, somewhere between, if we take this value right here and we subtract it from this 0.65 and then add it to this 0.65, it will give us a range, right? So if I do, for instance, 0.65 minus 0.067, all right, I get 58.3%, all right, 58.3% to, and then if I add these two, 0.65 plus 0.067 gives me 0.717, which is 71.7%. So between 71, there we go. So between 58.3% and 71.7% of the students want a coffee stand. Guys, that tells us right there that, most of the students want a coffee stand. So that'd probably be the way to go here. Now, if this thing dipped down below 50%, we might not know exactly. It doesn't matter if it goes up further. So if it said, oh, it's 49.2% to, I'm just making some numbers up, 71% or something like that. Yeah, I know this is mostly above, but still, there is a small portion that's below. So there's a possibility we may not know a majority of the students would prefer, whatever this data would line up to. Part of this whole thing, it says if Mr. Howe found a bag of that included 43 jelly beans in a random sample of 50, then determining margin of error at the 95% confidence. Okay, again, we use 95% most of the time, but not all of the time. All right. So again, we're basically going to take this formula here and we're going to multiply it times 2. Now, why this number? Again, because 95% gives us 2 standard deviations left and right. If it was 90%, this number would be different. And we even use a slightly different number here for 95%. You're going to see in a few minutes, especially in AP stats. You don't need to worry at this level where that number comes from. It's called a critical value, and there's some math that we can do to get it, but it's not really that important, right? In this class. So, 43 out of 50. Okay, so that's 43 out of 50 times 1 minus 43 out of 50 over, well, how big was our sample? Well, our sample was 50. And then we're going to take the square root of that and multiply it times 2. So this is going to give us our margin of error here. All right. So first things first, we're going to take our calculator out and we're going to do 43 divided by 50. Get 0.86. Now, if this is 0.86, think about what this is. That would be the thing that makes this go up to 1, right? So hopefully you see it's 0.14. So 0.86 times 0.14 gives me 0.1204. I'm going to divide that by 50, which gives me this decimal right here. I'm then going to take the square root of that number. So I take the square root of that number. All right. And then I'm going to times that number by 2. And I get 0.098, all right, which is 9.8%. All right. So we could say, well, there was 0.86. That was what we got by doing, the number that is 43 out of 50. So 0.86 plus or minus, and then we said that was 0.098. Again, this 1 says that 8, stay yourself. So 0.098, 0.098. So this right here is our margin of error. Not the whole thing. This is our, what we call our population mean or sample mean. All right. So that's how that works. Let's try some other ones. The Football Booster Club at Warwick High School surveyed to determine if they would rather have popcorn or sweet tea stand during football games. 440 out of 1,000 randomly selected attendees of a football game said that they preferred popcorn. A popcorn stand said preferred popcorn, but that sounds weird. All right, so determine the interval that represents the margin of error. Now, again, they didn't tell us, what confidence to have, so we're going to go with 95% confidence. So it's going to be, if they don't tell us, it's going to be a 2. All right, so, 440 out of 1,000, I could write that down here, but guys, if you put 440 out of 1,000, you knock that off. That's 44 out of 100. That's 44%. So we're going to go with 0.44 times, and again, I could put 1 minus 0.44, but I hope everybody knows that that's 0.56. okay? So we got 0.44 times 0.56 over, well, how big was the sample? Well, we talked to 1,000 people, and then we're going to take the square root of that and times it by 2. Okay, so with our calculator, 0.44 times 0.56 is 0.2464 divided by 1,000. All right, we're going to take the square root of that number, because that comes next, square root, and then we're going to times it by 2. And we get 0.031, and that's a 3, so we're going to leave that at 1. So it's 0.44 plus or minus, and then we're going to put 0.31, or 0.031, sorry, 0.031. Right? So if you think about that, if you took this and you added this to it and then subtracted this, so let's subtract this, we're not going to do this every single time, but 0.44 minus 0.031 gives us 40.9 to, that's a percent, 40.9% to 0.44 plus 0.031, and that gives us 47.1. So between 40.9% and 47.1% said they wanted a popcorn stand. They would rather have popcorn at the football games. All right, so that's less than half of the people. So if more than half the people did sweet tea, well, then that informs them that they want to go in this route rather than this route. Okay, but again, the margin of error is right here, 0.031, or 3.1%. All right. In New York City, 2,400 people were interviewed and asked if they purchased subway tickets instead of bus tickets. Of those interviewed, 1,943 said, yes, I purchased subway tickets over bus tickets. So we're going to do the same thing. Again, they didn't tell us what confidence to have, so we're going to do 95%, so that's going to make this a 2. So again, we got 1,943 over 2,400 times 1 minus 1943 over 2,000. We're going to divide that by, 2,400. We're going to divide that by 2,400. We're going to take the square root of that, and then we're going to times it by 2. 1943 divided by 2,400 gives me this value. And then we're going to times that by, parentheses, 1 minus, and then another parentheses, 1943 divided by 2,400. And that gives us 0.15415. We're going to divide that by 2,400 to do this part down here, which gives us this decimal. Now this says 6.4, but it does say e to the negative fifth, which means move this decimal 5 places to the left. So it's like 0.00006 and so on. All right. And then we are going to take the square root of that. Now, this particular mode does not have square root on it, but if you remember way back when, if we raise this to the 1/2 power, that is taking the square root. So if we raise this to the 0.5 power, we just took the square root of it. Notice that when we square root a number that's less than 1, it gets bigger, all right? And then we're going to times that number by 2. All right, so we get 0.016. All right, so 0.016 or 1.6% is our margin of error. Now remember this number here, we're going to need to round that. So let me just run that number one more time. 1943 divided by 2,400. And we end up with, that's about 80.95, so about 81%. So we're saying 81% plus or minus 0.016. Now, here it says determine if the 2,400 New York residents would be enough to people to say that in all of New York that your margin of error is valid. Um, there's a lot of people that live in New York, but one thing that you do notice is this is really, really um, a large percentage number. So we'd probably have to say, and I'm mixing my things here, so that's not really good. So it's 0.81 plus or minus 0.016, right? Or you might see it written as 81% plus or minus 1.6%, something like that. These mean the same exact thing. But this number's, I think you can safely say that a majority of New Yorkers um, purchase subway tickets over bus tickets. This is nowhere near 50%. So we are well, well, well above that. I mean, this would be 78.4% to 82.6%. Yeah, that's a pretty high percentage. All right. And then one more. A new drug was given to a random sample of 10,000 people with sleep apnea. The results showed that 8,500 of the people improved. Based on these results, can it be said that more than half of the people with sleep apnea will improve if they are given the drug? Justify your answer. Again, they didn't say what confidence to use, so we're going to do 95%, which would make this a 2. So we've got 8,500 out of 1,000, out of 10,000. So think about that, 8,500 out of 10,000. We're going to knock off these two here. 85 out, guys, 85 out of 100, that's 85%. Okay, so this here is going to be 0.85, and we're going to multiply that times 1 minus 0.85, which I hope you guys know is 0.15. All right, and then what's our sample size? Well, it's 10,000 people. And we're going to do this. Okay, so calculator. Let me go back to the other one because this one's works better for this one. 0.85 times 0.15 is this number divided by 10,000. It's going to make that number extremely small. We're going to take the square root of that number, and then we're going to multiply it times 2. And we get 0.007. All right. So, guys, this is 0.85 plus or minus 0.007. So that's a very, very, very small margin of error. It's very small. All right. So let's see how these are all related to each other. I kind of put all these together into a little table. I think it's really helpful to look at this table. I want you to notice something about this. So here's the last jelly beans question we had, the popcorn sweet tea at the football game, the subway bus in New York, and the sleep apnea question. This is the original sample proportion that we got for each one, 43 out of 50, 440 out of 1,000, and so on. This is the margin of error calculation that we did each time. This is the margin of error, guys. I want you to look at these margin of errors. 9.8% margin of error, 3.1% margin of error, 1.6% margin of error, and 0.07% margin of error. Take a look at that. What does anybody know why these margins of error are getting smaller? Anyone figure out what's the difference in this particular study here, and this one here, and this one here, and that one there? Here we got a 19.6% spread, so between 76.2% and 95.8%. Here it's from basically 41 to 47 or so. From here it's 79 to 83 or so, and from here it's only 84.3 to 85.7. So it's getting really smaller. What's happening here is the sample size is getting larger. Guys, I want you to think about this. As this number on the denominator gets bigger, it's going to make this number, regardless of what it is, much, much, much smaller. So, and that leads us into one of the main things about statistics is that as your sample size gets bigger, as you talk to more people, what happens is you get more accurate data. All right. So larger sample sizes equals more accurate data. That's how the basic concept. You talk to more people, you get more accurate data. All right. You sample more products coming off an assembly line, you're going to get more accurate data based on the percentage that is faulty, something like that. Larger sample sizes produce better data. All right, so what we're going to do now is a little bit different. This week, for those of you guys sticking around and watching the video and being completely bored by me, we're actually going to go through those questions together. All right, so we reached the end of the topic number 7. So now I do understand that your questions might be in a different order than mine. So as we go through these, write down what the answers are. When you go ahead and go on there, you should be able to get a 100% relatively easily. As far as the whole valid invalid attempt this week, it'll be kind of interesting. I'll know it's a valid attempt. Um, if it's a very short attempt, if you get a 100, based on the fact that if you get a very short attempt with a 100, that means you were hopefully watching this video. If I get a very short attempt of a 0 and then they turn around and get a 100, that means students aren't watching the video at all, because they never saw me go through these questions with you. So one of the questions in the first topic is your statistics class conducted a random survey regarding the cafeteria food offered at your school. You surveyed 150 of the 875 students in the school and you found the following. Now, again, this is the data from the 150, not all of the 875 students. So 39% thought that the proportions were too small. 23% of those sampled thought there was not enough variety. 12% thought it was too salty with no space for some reason. And 26% thought there was not enough healthy options. So, based on your survey, what data can you extrapolate to the entire student population? Select all that apply. This is very important right here. Extrapolate to the entire student population. What they're saying is you take your data from a small, sample of data, and then you expand it out to the entire student population. All right. So, do 228 students of the entire student population think that there are not enough healthy options? Well, let's go back up and look. So, not enough healthy options is 26%. All right. So 26% of these 150 students thought that there were not enough healthy options. Now, if that's a valid sample there, random sample, we should be able to expand that out to the student population. So if we need to find out what 26% of 875 is. So 875 students times 0.26, that's 26%, equals 227.5. Well, this is 228. That appears to me to be a good answer. All right, so we're going to say, yeah, that's one of them. All right. Now it says 39 students think that there are not enough healthy options. Well, we just said 228. What the 39 is, that would be probably, I would guess, 26% of this. All right. So let's see, 150 times 0.26. And yeah, we get 39, but again, this was about the entire student population. This answer here is not about that, so no, we're not going to pick that one. Okay. So what about 201 students think that the food in the cafeteria is too salty? Well, let's see, 12%. So we're going to take this 875 and we're going to multiply it times 0.12. 875 times 0.12. And we get 105 students. So we go down here and we go, that doesn't seem right. That's 201. Nope. 341 students think that the proportions or the portions are too small. All right. Too small is 39. So 39% of 875. 875 times 0.39. And we get 341.25. So we're going to say, yep, that appears to be the correct answer. And 35 students think that there's not enough variety. So we go back up there to not enough variety. That's 23. So we're going to take 23% of this 875. 875 times 0.23 gives us 201 or so. Nope, that's wrong. So we've got our two answers, right? The 228 and the 341. The next question, or it might have been your first question, depends on what order you get these in. During gym class, you are responsible for recording the time in seconds it takes for each student to run the 100-meter dash. What is the mean time to run the 100-meter dash for the students in your class? Well, guys, anybody remember how to get means? We add the values up and divide by the number of values that we have. So we're just going to take and add these values up. So 17 plus 12 plus 15 plus 13 plus 12 plus 18 plus 21 plus 17 plus 14 plus 16 plus 15 plus 20 plus 19 plus 13 plus 16. So you get a total of 238. There were 15 pieces of data, so we're going to divide by 15. And that's going to give us a mean time of 15.866, and I believe it's rounded in your answers, so pick the answer that's closest to 15.866. Should be 15.9. All right. The second part of this says, if you were to record the times of 15 students in the next class as they run the 100-meter, would you attain the same mean as you did in your class? Guys, 15 new students running the 100-meter dash. Are we going to get a mean, do you think, of 15.9 seconds? Hopefully you recognize, no, new data is going to give us a new mean. All right, so the answer there is going to be no. All right. It says, let's say the teacher gave you a list of names and times for 15 students in the next class, and you calculate a mean of 16.7 seconds. What is the mean time to run the 100-meter dash for both classes? Well, guys, that's really easy. If you have means to work with, you can average those means. So if the first class averaged 15.9 seconds and the second class averaged 16.7 seconds, if you add those together, 15.9 plus 16.7, you get this value. Well, you just added those two numbers together, and then you're going to divide it by 2, and that will average those two means. So you're basically taking the average of the averages, and we get a mean of 16.3. All right, and the last question, or again, they might be in different orders. So during homecoming week, your school facilitates several competitions for a chance to win a prize. One of the competitions is a guessing game. There is a large clear fish tank with 2,000 small rubber balls in it. The balls are blue and yellow, your school colors. Imagine that. To win the prize, you must correctly guess the proportion of blue to yellow balls. You have 2 minutes to make your guess. Obviously, this is not enough time for you to count all 2,000 balls, but you do have time to take some random samples. In your 2-minute time limit, you create the table below. Wait, what a nerd. Okay, so sample number 1, 2, 3, 4, and 5. The first time they pulled out 10, then 20, then 35, then 50, then 75 balls. The student must have worked very fast to get this done in 2 minutes. Total number of balls they found out with these, and then we're going to fill out these percentages, and then we're going to make a best guess. All right, so the first time they only took out 10 balls, and they got 2 yellow balls in the sample. That's 20%. So the next time it's 4 out of 20. So we're going to take our calculator and we're going to do 4 divided by 20. And so the second time we got another 20%. All right. So that's 20% or 0.20. I'll do 20%. The next time 11 out of 35. So we get our calculator out. 11 divided by 35. We end up with about 31.4% of yellow balls. 17 out of 50. 17 divided by 50. That gives us 34%. And then finally, 26 out of 75. 26 divided by 75. And we get 34.6%, or about 34.7%. 34.7%. All right. So what this is relying on here, guys, and you have to choose from 20%, 30%, 34%, or 30%. What this is relying on is as this gets bigger, as the sample size gets bigger, we get more accurate data. We've talked about that. All right. So really what we want to kind of focus on is maybe the couple largest guys, 34%, 34.7%. Looks like this is the one right here. Okay. What is your best guess of the proportion of yellow balls to blue balls in the tank? About 34%. All right. So that's the end of that check your understanding for topic 7. So now we're moving on to topic 8. Okay. One of the main differences from topic 7 is that we've been working with summary statistics. You know what I mean? We haven't been talking about the individual raw data. Sometimes we have to work with the raw data. So sometimes we're going to replace this with this. And this is what this is going to do, is this is going to give us the standard deviation. We're going to use this very little, guys. We are going to use this very little. So even though this thing looks absolutely crazy, it's not that bad. Each thing has a different part. I'm going to show you how to do this with a set of data. All right. So don't worry too much about that. This is actually the second part here. I know that first part had a lot to it, but the second part really doesn't have a ton. All right. So here we're going to use some raw data. So assume you want to do some summary statistics when you are shopping for a new smartphone. A sample of 10 different smartphones has been selected at random. Their prices are listed low to high in this table, and you want to find out the standard deviation and the margin of error for all smartphones from this raw data. So we've got 10 different smartphones. Now, the first part of this says we're going to take whatever the sample value is, and we're going to subtract it from when you see X bar, that is the mean. So we're going to take all the phones, and we're just going to order them. You don't really need to order them, but it makes it a little bit easier. So we got 249, 329, 419, 599. Again, there are 10 phones here, 10 phone prices. We find out the mean by adding these up and dividing by 10 is $636.70. Now, what we do for each of these is we take this value and we subtract from it the mean. All right, so 249 minus 636.70 is negative 387.70. And then we do this for each one. This number minus this number is that number. And this number minus this number is that number. And this number minus this number is that number, and so on. And we do this for all of them. And notice some of these are negative. That's for the phones that are here to here. These are phones that cost less than the mean. And then the ones from here down to here are going to be positive, because when you do 649 minus 636, you're going to get a positive number. And you do this all the way down. And then what you do is you square these values. Now, squaring these values turns them all positive. A negative times a negative is a positive, negative times negative, positive. Down here, a positive times a positive is positive. And then what we're going to do is we're going to add these up. Guys, this little symbol right here means a sum. So we're taking each x value, subtracting the mean from it, and then we're going to square that value, and then we're going to add all those values together. We're going to sum those values together. Now, the denominator here, n minus 1, n is the sample size. We had 10 phones here. So this is going to be 10 minus 1, which we know, of course, to be 9. All right, so what we end up with is 532,364.10, 532,364.10. That's our numerator. Our denominator is 9. And then what this is going to do is it's going to give us our standard deviation. Okay, so we're going to take our calculator out. 532,364.10. We're going to divide that by 9, which gives us 59,150. 51, and then we're going to take the square root of that value, and that gives us 243.21. This is dollars and cents, so it's appropriate to round at the second decimal. 243.21. So what that means is if we wanted to do one of these normal distribution models like this, the number that goes right in the middle would be 636.70. And then we go one standard deviation up to three standard deviations, and then 1, 2, 3 to the left. And you would take this value and repeatedly add it to move to the right and repeatedly subtract it to move to the left. All right. So I'll just give you one of these values. I'm not going to do them all, but 636.70 plus 243.21 is 880.91. So that's the number that would be right here, 880.91 right here. All right. And then you would add it again to get the next one, add it again to get the next one. If we had a lot more phones here, by the way, we would end up with a little bit more accurate standard deviation. Remember, larger data sample sizes produce better data, more accurate data. But that's how you can calculate standard deviation for your own. It's this formula here that looks super crazy and is a lot of work, but all of the work is very simple. We got some subtractions going on. We've got an averaging going on. We've got a squaring going on. We've got a bunch of adding all these numbers together, and then we divide by a value and take the square root. It's really not that hard to do. Okay, and then we're going directly into our questions here because we really haven't learned anything new other than that thing right there. And I checked in the check your understanding questions. They don't even actually ask you to gather any raw data. So you really don't have anything new that you need to know. So, right. So it says Carter Davidson High School is voting on a new logo for the school. Again, this is your check your understanding. I don't know if it's your first, second, or third question for topic 8. In a poll that sampled 1,000 students in the school, the results showed that 580 of the students liked logo A, while the rest liked logo B. So it says, what is the margin of error in this poll if the surveyor is on a 95% confidence interval? And we're going to use a z-score, a critical value of 1.96. Notice how we were using 2 before? This 1.96 is actually a little bit more accurate. That whole 68, 95, 99.7 rule is actually kind of like an estimate, right? It's not 100% accurate. It's close. So this value is just a little bit more accurate than a 2. All right, so we're going to do the same thing that we did before. We're going to do the whole 580 out of 1,000 times 1 minus 580 out of 1,000 over our 1,000 sample size. But this time, after we take the square root, we're going to multiply it times 1.96 because we're just trying to be a little bit more accurate with our value. All right. So remember 580 out of 1,000, guys. 580 out of 1,000 is really 58 out of 100 or 0.58. So I'm going to put 0.58 here just to make it easier. And if that's 0.58, then this over here is going to be 1 minus 0.58, which we know is 0.42. Okay. All right. And then I'm still going to times it by 1.96. So we got 0.58 times 0.42 divided by 1,000, the sample size. And then we're going to times that, or sorry, take the square root of that. And then times that by 1.96. And we get 0.3059, right? Or, I believe one of your answers is 3.06%. Okay? If you think about that decimal right there, move this decimal 2 places, 1, 2. And then what does this 9 say to this 5? Hey, round up. Okay, so 3.06%. All right. So it says, with that margin of error in mind, what is the range of students who like logo A? All right. So the range of students that like logo A. What we're going to do, we know that the very middle, the sample proportion is 58%, right? 58%. So we're going to take that 58% and we need to add and subtract this value to it. All right. So first, let's subtract it. 0.58 minus 0.0306, and that's 54.94. All right. 54.94%, 2. And then we're going to take this 58 and add this. And I'm going to do the second one slightly different. I'll do the 58 plus 3.06 because you can do it as percentages or you can do it as decimals. It doesn't really matter. So 61.06%. Okay, so this should be your answer on that second part on that particular question. All right. Jumping to the next question. A local restaurant is surveying their customers about their dessert menu. They want to know the proportion of customers who like their chocolate lava cake. The owner of the restaurant wants the margin of error to be within plus or minus 2% at a 95% confidence interval with a standard deviation of 0.5. How many customers should they sample? So, guys, with this particular question right here, we do have one little piece of information that is missing. We don't know how many people actually like their chocolate lava cake. All right. So, one of the things that we learn in AP Stats, and I don't think they covered in the Algebra Nation video. I didn't watch the Algebra Nation video, but if you are unsure, notice that on this last one we had 58% because we had, 580 out of 1,000. All right. Now, if you don't know what the percentage is, assume it's 50%, because that's going to give you the most accurate data. So when we do our formula this time, we're going to do 0.50, right? And we're going to multiply that times 0.50. Now, we're not multiplying that because that's what this is. That has nothing to do with this. This is kind of like a throwaway little extra thing that they threw in here, all right? So we're going to do 0.50 times 0.50. This is kind of like, the p hat times 1 minus p hat. Right? So if our proportion is 50%, then 1 minus 50% is another 50%. Now, what we don't know, this is where the sample size normally goes. This is the thing that we don't know this time. So we're still going to have to do this math, right? And if it's 95% confidence interval, we're still going to do 1.96. Remember, in the last section, we were using a 2. Well, if you want to be a little bit more accurate, you want to use 1.96, okay? And so we're going to go ahead and we're going to run this calculation. We're actually going to do some algebra and solve this for x. So, and what do we want the margin of error to be? Well, it says 2%. So how do we write 2% over here as a decimal? 0.02. So all we're going to be doing is we're going to be solving this for x. All right. So the first thing that we can get rid of is this. So this is 1.96 times this. So we're going to divide by 1.96. That's going to cancel this out. So we're going to divide this side by 1.96. So in our calculator, we're going to do 0.02 divided by 1.96. And that gives us 0.0102. And I'm just going to leave that number in my calculator. I'm not actually going to write it. Well, I'll write down a shorter version of it. 0.0102. And this number is really kind of interesting if you look at it. It's like 1 and then a 2 and then a 4 and then an 8 and then a 16 and a 32. It's kind of like adding or doubling each time, each decimal. I don't know why. It's just kind of weird. All right. Now on this other side, we still have this whole square root of, and if you want to go ahead and multiply this out, you can. 0.5 times 0.5. I'm not going to quite do it yet because I still have this value in my calculator. All right. So 0.5 times 0.5, which hopefully you guys know is 0.25. And now we're going to get rid of this square root. Well, what's the opposite of square root, guys? Quick. Squaring, right? So this is going to cancel this, but that means we've got to square this. So let me go back to my calculator. I'm going to take this value that's already in there and I'm going to square it. All right, that gives me this one. Notice this number got smaller. See this e minus 4? That means take this decimal and move it that way 4 places. So this number did get smaller when we multiply numbers times themselves less than 1. They get smaller. And so what that leaves us is 0.000104, and it continues on, equals 0.25 over x. And so the last thing that we need to do is we need to, you know, it's helpful to understand. Remember, this is kind of like a proportion. We can switch these two. So really, what are we doing? We're doing 0.25 divided by this value. All right. So 0.25 divided by this number right here. So 0.25 divided by 0.000104. And I know there's some other stuff, but this decimal is so far out at this point, it really shouldn't matter. 2,403, 2,404 or so. Now remember that I did round this. Okay, this decimal kept going forever. So by rounding it off, I'm off a little bit, but I hope you can see I'm not off by enough to matter. Right? So when you look at this answer and you go, which one of those numbers match up with this? Well, it looks like we're going to be talking to 2,401 people, right? And that should be enough to talk to. All right, the next question. A recent survey asked people how many cups of water they drink each day. Out of the 600 people who responded to the survey, 64% of them said they drink between 0 to 5 cups of water per day, and the remaining 36% said they drank 6 or more cups of water per day. What is the margin of error if you use a 90% confidence interval? Well, this time we're not going out as far. So if you think about it on our little thing here, here's our mean. Here's one standard deviation out. Here's 2. Here's one standard deviation this way. Here's 2. From here to here would be 95% of the data, right? In other words, 2 standard deviations out, all right? Well, if we're only going to do 90%, we're not going to go out as far. So we're not going to go as many standard deviations out as far. How far are we going to go out? This much, okay? So we're still going to do the same formula, except when we do our 0.64 times our 1 minus 0.64, which they were so kind to give to us, it's 0.36. We're going to divide this by our sample size, 600, and take the square root. But this time we're going to multiply it times 1.645. Okay, that's the value that they gave us. So we're going to go ahead and just work this out and see what we get for our margin of error. All right, so 0.64, move this over, 0.64 times 0.36 divided by 600, take the square root, times it by 1.645. That gives us a margin of error, let's say about 3.2%. All right, right, 3.2. All right, 3. Oops, my computer's freaking out. 3. Hello, computer, stop being weird. Hey guys, I don't know why my recording software or my calculator or something was freaking out there, but anyways, we put 3.2% down here. That was our answer that we ended up with. So the last part of the last question, just very, very quickly, just like before, except for the fact that we are, we're looking at a margin of error of 2%. And we're still going to do the same thing. We're still going to say 1.645. We're still going to multiply that times 0.64 times 0.36 over x this time, because we don't know. But we do want the margin of error to be 2%. Again, 2% written as a decimal is 0.02. So you just have a little bit of algebra to do. All right, again, we want to get rid of this right here by dividing, because currently it's being multiplied. And the other thing that we can do really quick here is to go ahead and multiply this out as well. So I think I'll actually do that first. So 0.64 times 0.36, 0.64 times 0.36 gives me 0.2304, 0.2304 over over x, take the square root, and then over here 0.02 divided by 1.645. 0.02 divided by 0.02 divided by 1.645 gives me kind of a long decimal. Now, I'm not going to write this whole thing down. I'm going to do the old ... thing. 0.01216, let's say. All right. And then what I need to do is I need to multiply that. I'm sorry. We want to get rid of the square root symbol, so the opposite is squaring. So we're going to square that value. So in my calculator, I'm going to square that. All right, again, this number actually got smaller because we got e to the -4, so that means put a decimal here and then move it 3 places to the left. So this left side is kind of turned into 0.00014, and then 7 ... equals 0.2304 divided by x, because this canceled out that. And then again, if I make this a proportion, I'm allowed to switch these two. Okay, so what I'm doing is 0.2304 divided by this value. 0.2304 divided by 0.00014. And actually, I'm going to put an 8 here because the next decimal after that would have caused that 7 to go up to an 8 anyways. And we get 1556.75. Again, this is a rounded answer from a rounded value because I didn't have this whole value in the calculator. So, what numbers as close to this as possible? I hope you see an answer that is 1,559. So that's how many people we need to survey in order to make the margin of error be 2%. All right. And that's it for the week, guys. Again, if you paid attention to this whole video and you walked through these questions with me, you kind of already know what the answers are. So you should be able to get a 100 pretty quickly. I'm going to notice which students aren't paying attention by seeing which students are, again, doing it the old way, the old crappy way. Just busting through the answers or questions really quick, answering them wrong, but seeing what the correct answers are, and then turning right back around and getting a 100. And of course, hopefully you guys don't do that. All right. Well, guys, have a great day and a great week, and I'll be posting another video next week. All right. Thank you. Bye.